I'm Merlin Bicking, and my talk is Listen to Your LC Instrument. It's trying to tell you something. Let's get started. We will start with a review of a few concepts. Dwight has already covered the importance of pressure information, and we'd like to add to that. But we'll spend most of our time talking about solving retention time changes. We will introduce you to change ratios, give you some other tools, and then look at some case studies. So your instrument is talking. What's it saying? Well, these are some of the data streams that are coming out of a typical HPLC. You can see there are several pieces of information, and there are many more if you look for them. But it seems like a lot of noise, but it's not. These are all bits of information that we can use, especially if we're troubleshooting problems. And that's what we'd like to discuss with you today. Our first concept is the void time. This is the time required to pump one void volume through the system. We can calculate this if we know the void volume and the flow rate. This is the beginning of the chromatography. And any component that elutes in the void time spends 100% of this time in the mobile phase. That is, there's been no stationary phase interaction. It came through in the minimum time, no stopping along the way. If we don't know the void volume, we can estimate the void time using two different methods. One is using the system or vacancy peaks. These are those small disturbances that appear at the beginning of the chromatogram, and they can be used to estimate the void time. They are generally caused by either a difference in the composition between the mobile phase and the sample solvent, or they're caused by unretained components in the sample. These are two different examples of those void time disturbances. It can be a simple pattern, as you see on the left. It can be more complex, as you see on the right. We could also inject uracil. That's a fairly common void time estimator for C18 and many other reverse phase columns. Our next concept is the retention factor K. This is a mass distribution constant. It tells us how much time the compound spends on the stationary phase, and it used to be called the capacity factor K prime. It describes retention as the number of void volumes represented by the adjusted retention time. You can see that in this equation with the term on the right side there. The retention factor controls retention. A larger value means during the separation, more molecules are in the stationary phase and the retention time is larger. We generally adjust operating conditions so that K is between 2 and 10 for an isocratic separation. So when we calculate K, the retention factor, what does that really mean? Well, we can calculate it theoretically if we know what the value is. What is the percent in the stationary phase for that given value of K? In this chromatography example, you can see a number of peaks. Now we have something eluting at the void time, and by definition, something that elutes at the void time has a K of 0. And we can see peaks that elute near the void time have K values less than 1, and out to the last peak, which has a K value of 13. And I've also given you a scale at the bottom that indicates what the appropriate K value would be for that retention time. This might be another way of looking at what this means in terms of the chromatography. Remember, this is the mass distribution constant, the difference between the number of moles in the stationary phase and the number of moles in the mobile phase. And you can see for the later eluting peaks, most of the molecules at any given time are in the stationary phase. The next issue may go by different names, but I was always taught this to be the general elution problem. We know for isocratic separations that the number of theoretical plates is approximately constant for a system. This is, of course, the definition for a theoretical plate, retention time over the peak width. As retention time increases then, to keep n constant, the peak width also has to increase. So what this means is early eluting peaks are narrow and often poorly resolved from other peaks. The later eluting peaks then are better resolved, but they become wider and the peak height decreases. Now remember, later eluting peaks also have a larger value for K. So you can see in this chromatography example, the early peaks are more narrow The peak heights are much larger, and peak height steadily decrease, peak width steadily increase throughout this. So we can summarize this in a simple take-home message. The longer molecule stays on the column, which means that the K value is larger, the wider and shorter it gets. Dwight has already discussed pressure effects in LC, and I wanted to add a few extra comments relative to our perspective here. HPLC pumps are constant flow devices. That means that they will work as hard as they need to produce the desired flow. The pressure then is an indication of how hard the pump is working to produce that flow. So pressure changes with a change in any of these individual parameters. So what this means is that pressure is one of our primary diagnostic tools for troubleshooting HPLC problems. So from a troubleshooting perspective, when we see a change in pressure, we need to look for a change in one of these parameters. And that's really one of our keys to troubleshooting issues. Okay, it's finally time to talk about troubleshooting. So there are many ways to approach troubleshooting for LC. This is the approach I use. This is my troubleshooting matrix for HPLC. Across the top, we have a number of symptoms, and these are the more common symptoms. Certainly not everything you run across, but this is a great majority of the things you're likely to see. And then on the side, we have a list of components or causes or parts of the system that might be responsible for these particular symptoms. Okay, let's start with a little philosophical comment. So the first step in troubleshooting is to identify the problem or symptom that you have, right? Pretty obvious first step. The second step is also important. The second step is to determine which components are not likely to be involved. So if you look at this troubleshooting matrix, you can see that not every combination of symptom and component has a red box filled in, which means they are not responsible for that particular symptom. So for example, if we had a retention time problem, which indeed is we are going to discuss today, we can determine that it's not likely to be the sample, it's not likely to be the injector, it's not likely to be the detector, and it's not likely to be the data system. So we have eliminated almost half of our system just in these first two steps. What is the problem and what things can I ignore? Okay, so let's dig into retention time changes. So there are generally three categories of changes or problems we'll observe. Sudden changes, drifting over the course of several runs, or erratic or just completely unstable retention time. And from the troubleshooting matrix, we've identified the mobile phase, the pump, the column, the tubing, and the environment as possible causes. Okay, so let's look at some more specific possibilities for these changes in retention time. And this is a typical list that you might see from a number of different sources. And we'd like to look into this in a little more detail. For this talk, we're just going to focus on some of these, and these are going to be issues related to flow rate, mobile phase, and temperature. These are all possible problems that can show up, and we're going to discuss ways that you can identify and distinguish between these different causes. So let's step back and take a more general look at why retention time will change. If we have a change in flow rate, that's going to change retention time. Similarly, changes in mobile phase composition and temperature will cause a change in retention time. And of course, if we make some changes to the system or we have some other settings, they can have an impact. Now, how does this impact the data streams that we might expect from our instrument? Well, when the flow rate changes, we know the retention time will change, but the void time also changes. And because of this, the value for K, the retention factor, does not change. When the composition or temperature change, the thermodynamic parameters, we'll see the void time does not change, but the retention time does change, and thus K will change. So these are all examples of patterns in failure or patterns in change. And successful problem solving is all about recognizing patterns. If you can find the pattern, you can usually find the cause. Okay, let's dig into these changes in a little more detail to determine if we can figure out a pattern that might emerge. This is the fundamental retention time for chromatography. If we take parts of this and look at it from a settings perspective, we can get this rather messy looking equation. It's more complicated than we really care to deal with, but there are only a couple parts of this that we really care about. And if we strip out things we don't care about, we can see that the flow rate shows up as a cause of change. And if the flow rate changes, it produces a simple inverse linear change in retention. And without worrying about the details in the math, we do know that if the composition changes, or if K changes, and that might also be caused by temperature, the change causes a logarithmic change in retention, which is going to be complex and nonlinear. So with this information, we can now start looking at our data, and we'd like to compare the good and bad chromatograms. So we're going to calculate something I call the change ratio, and we're going to compare the corresponding peaks in the good and bad chromatograms. And we can calculate these ratios for the retention time, the area, and the height, assuming we have those measurements. And we're just going to simply define the change ratio as the ratio of the bad value over the good value for any of these parameters that we're measuring. So let's say we had a flow rate change in our system. How might we identify that using the change ratios? So for example, we have a chromatogram that looks like this, or two chromatograms, one good, one bad. We can look at the change ratios for the retention times and notice if the change is similar for all of the peaks or does it change. So if the change ratio is constant or at least very similar for all peaks, then the problem is caused by a simple flow rate change. This would be an example of data using this. Notice the absolute differences in retention times are different for the four peaks based on their actual retention times. However, the ratio or the relative change is constant for all of them. This only happens with a flow rate change. So what happens if your composition changes? Here's another chromatogram with a different pattern. Let's calculate the change ratios for the retention times and look at the values, and are they similar for all the peaks or are they changing? So if the change ratio is not constant, but it is trending, then the problem is likely caused by a composition change. This would be the complex logarithmic change that we talked about a few slides earlier. Change ratios for this example are shown here, and you can see they are not constant and they are increasing in this particular series because retention is increasing. In this case, we have a weaker mobile phase, causing longer retention. Now, there is another possibility that we can discuss and that we have to consider. And what happens if both the mobile phase changed and the stationary phase changed? And by changing, we mean the chemistry actually changed. This is what we call a selectivity change. In this particular case, the change ratio for retention times is not likely to be constant, and it's also not likely to be trending. So then a change in selectivity is one likely explanation. Of course, there are other problems that could cause this as well, but normally we will say selectivity is one of the most likely changes. So this would be the change ratios in this particular example. You can see that the first two peaks elute later in the bad example. The third peak does elute earlier, and then the fourth peak elutes a little bit later. Clearly, there is no pattern in the retention times. So now we know what information we need. We can start using this information to draw conclusions about our particular problem. All the change ratio patterns can now be used to help us identify the cause. Now, in your particular data set, you may not have all of this information available, but even a partial pattern match can be very helpful in identifying the cause. So, for example, if you have a flow rate change, if your flow rate decreases, the retention times increase in constant proportion, the areas increase in constant proportion, but the height ratios do not change. If you have a composition change, going to a weaker mobile phase, all ratios increase, but not at the same level. The area ratios do not change, and the height ratios decrease, and again, not in constant proportion. And finally, if you have a selectivity change, all bets are off. There's really no pattern. So if you look at that previous slide with the change ratios, you might ask yourself, why does the area increase when the flow decreases? Well, there's a simple reason for that. The data system collects data at a constant rate. This is independent of everything else in the system. Once the run starts, it's collecting data at a specific data rate. So we do know that with a normal flow, we might get a certain peak width across the start to finish. There might be a certain number of data points that generates area and height values. If we slow the flow down, the peak spends more time going through the detector because the flow rate is less. The detector really has no way of measuring this. So more data points are collected and it generates a larger apparent peak area. So in this case, our peak width increases, our number of data points increases, and the area also increases. You'll notice the height does not change much. So of course this brings up the next question, why doesn't the height change when the flow changes? So for a concentration sensitive detector, and this would be absorbance and fluorescence, refractive index detectors for example, the concentration of analyte in the detector at the maximum does not change when the flow changes. So the apparent peak height does not change. In this particular example, you can see the flow rate change causing a change in retention time, but the peak heights are approximately the same. Now the same does not happen when we have a composition or temperature change. These thermodynamic parameters are changing the value for K, which means the chromatography has changed. So what you see here is a result of the general elution problem. As we go to more and more retention, K increases, the peaks get wider, and the peaks get shorter. So if you compare the change ratios on the left side, which are nearly identical and unchanged for flow rate changes, with the peak height change ratio on the right side, again, you see a steady decrease in the change ratio for height. Again, because the peaks are getting smaller or shorter because they are staying on the column longer. They're also getting wider. Of course, we do have two more data streams that we can look at, and we can use these pieces of information for drawing more conclusions. So we talked about pressure and pressure plots, and sometimes comparing the good and bad pressure plots can be a very insightful way of identifying a problem. For example, these are two pressure plots that are nearly identical. Clearly, there are very few changes or only random changes and differences between those two injections. On the other hand, these two injections have considerably different pressure plots. Again, the units here are in bar or atmospheres. Similarly, we can look at the vacancy or system peaks at the void time. As we mentioned earlier, they elute at the void time in the void volume and are only affected by flow rate. So if the flow rate hasn't changed between two injections, those squiggles should overlap almost perfectly, as they do here. If there is a change in flow, we will see a definite change in the location of those patterns for the vacancy peaks. So now that we have all this information, we can use it with some case studies. So here are two injections, good and bad. We see an increase in retention time ratios. I've expressed them as a percentage here rather than a simple ratio. And they're about constant, similar increase for area, no change in height. This looks like the pattern for flow changes. And if we look at the pressure plots, they are indeed different. The red pressure plot is lower than the good one, the green one, which would be consistent with a slower flow. If we overlay the vacancy peaks, we see the red ones are also later. So indeed, this is a flow change. In case study 2, we have a different pattern. So now we see the retention times are increasing and they are trending to larger values. The areas are approximately constant and the height is now decreasing and it is trending to smaller values. So this looks like a thermodynamic change. We see also a change in the pressure plots. In this case, the bad pressure plot is at a higher level. If we look at the vacancy peaks, we see they're approximately overlaid. There are some very minor differences, but within the normal variability of an instrument, those are probably the same. So we would say there's not a flow problem. This is likely to be a temperature or composition change. Another case study, again, a similar pattern, an increase and a trend upwards in retention time. Areas are about the same with no change, and height is decreasing. Pressure plots, in this case, the red pressure plot is higher. Again, these are all consistent with a thermodynamic change, and we see the vacancy peaks are overlaying pretty well, so there's no flow issue. Again, we would then guess this is a composition or a temperature change. In this case, it is in fact composition. You'll find that changes in composition cause significantly larger changes than the changes in temperature. Going to the next scenario, okay, we have a pretty scattered output here. So we have a wide range in retention time changes, no real pattern there. The changes are different for the area numbers and the changes are not consistent for the height. So there really is no pattern here. The pressure plots are quite spectacular in the difference here. Clearly there's a huge difference between these two injections as noticed by the pressure. This is likely to be a change in mobile phase from something fairly non-viscous like acetonitrile to one of the alcohols which are more viscous and produce higher pressure. The other indication that it's a change in selectivity would be the vacancy peaks. You can see there's a huge difference in the pattern for the bad injection, means that the difference between the sample solvent and the mobile phase is significantly larger in this particular example, meaning the change was most likely a change in the mobile phase, not, for example, a change in the column chemistry. Finally, you might be in the pharmaceutical industry and you say, hey, I've only got one peak. How can I use all of this? Well, all hope is not lost. In this particular case, we have two different runs we're comparing. Retention time is larger for one data set. Peak heights are approximately the same. Fortunately, we do have access to the vacancy peaks, and we can see there is a difference in the pattern for the vacancy peaks, and clearly this looks like it is a flow rate change. And similarly, if we look at this pattern, it looks very similar. The retention time is larger for one peak. You will notice the peak height is slightly smaller for the later eluting peak, And you do notice that the vacancy peaks do look like they're overlapping. In this particular case, I don't see any particular flow rate change. So this difference is likely caused by a change in the composition of the mobile phase or the temperature. So we can wrap up this talk by just reminding you that your instrument is always talking. You just have to listen to it. There are many data streams to monitor, and in most work, in most successful analyses, you won't need most of them. But we want to have them available because when problems occur, you must know where to look for clues and how to interpret that information.